In the previous video, we had discussed about the Poisson's ratio, and we had already found out the Poisson's ratio's theoretical value range is from plus half to minus 1. That means the practical value is plus half to 0. Now, a question can be given that Poisson's ratio, to derive the Poisson's ratio, the value or exact value of the Poisson's ratio when volume does not change due to elongation. Now, if we take the volume to be V is equal to pi r square L, that means considering the wire to be a cylinder, cylinder of length L and the radius of the cross sectional area is R. So V is equal to pi r square L. Now, differentiating both sides, we get dV is equal to, now pi is a constant, we take it out. R square and L are two variables. That means we have to derive get the derivative of this in the form of U into V. So 2R dr into L plus dl into R square. So dV means the change in volume. Now, if the volume is constant, if this term is a constant, that means dV must be equal to 0, because you know that dV or the derivative of any quantity which is constant is 0. So dV must be equal to 0 if volume is a constant. So 2RL dr plus R square dl. From this we get dr by r is equal to dl by, I can think there will be a minus sign here, dl by 2 pi 2l, because if we take 2rl dr onto the left hand side, 1 r gets cancelled out, so minus dr by r is equal to dl by 2l. Now minus dr by r by dl by l is equal to half. Now why did this negative sign come into picture? This negative sign indicates that if L increases, then R decreases, because if we pull this wire by a force F longitudinally, the radius or the diameter will decrease, hence reducing the radius, and the length L will increase. So I have written negative sign indicates that L increases as R decreases. Now what was dr by r by dl by L? This was the value of Poisson's ratio. Now we can take only the magnitude, so dr by r dl by L is sigma, or the Poisson ratio is equal to half, or rather 0.5. This is for the material of a wire which does not change its volume due to elongation. Now, work done in stretching the wire. Now, this is a very important topic, you can say, and a question comes, that is a proof. You have to prove a statement, that is elastic energy density. Elastic energy density is equal to half into stress into strain. You have to prove this relation. So let us start a little bit explicitly. That is, try to first understand what the word elastic potential energy means. What is the meaning of the term elastic potential energy? As I have already told you, that when a body gets strained, that means an external force is acting on a body, the body gets strained, and internal reaction force develops inside the body. This internal reaction force, so we name it as stress. Now one question can come, whether strain or stress is a fundamental aspect. I repeat the question, whether stress or strain is a fundamental aspect. Which one is more fundamental? Every student can give the answer as stress is more fundamental than strain, but that is wrong. You have to state that strain is more fundamental than stress, because external force when applied on a body, the first thing that happens to a body is strain. That means the body starts to deform. Now, as the body starts to deform, the internal force of reaction comes into play to prevent that deformation. So, more fundamental is strain, less fundamental is stress. Now, as I was explaining to you, that elastic potential energy, now the applied external force does some work against this reaction force to produce deformation in the body. I repeat the statement: the applied external force does some work against this reaction force to produce deformation in the body. Now, what does this work? Where did this work go? Where did this work go? External force. I'm stating that external force, when acted on a body against reaction force, because reaction force will try to prevent any deformation in the body. So external force will try to act against this reaction force to produce deformation, or rather permanent deformation, you can say. Now, external force is doing a work. So external force is doing a work. Where did this work go? This work is stored in the body as potential energy, known as elastic potential energy. This work done by the external force to produce deformation is stored in the body as elastic potential energy, and if the external force is withdrawn, what happens when the external force is withdrawn? Then the internal reaction force, that is stress, ceases and or stops, and this potential energy is converted into heat energy. Very important, you have to learn this thing, that when the external force is withdrawn, let me write it. External force is withdrawn. External force that was trying to deform the body is withdrawn, is removed. Then the internal reaction force ceases or stops. Internal reaction force stops or ceases. That is, you can say that stress ceases and this potential energy is converted to heat energy. Now we are moving into the part of elastic energy density. Now for that, let us consider aware. Again, aware of length, let's suppose L. The force applied, and the wire increases in length. Let the original length be capital L, and this was the original length, and the increase in length be small l. This was the original length L, and the increase in length is small l. Now if one end of this rod is rigidly attached to a plane support, suppose the rod is hung from a point, this wire is this one. So if we hang this wire from a point, this is the fixed point. So within the elastic limit, the elongation is directly proportional to the applied force. Elongation is directly proportional to the applied force within the elastic limit. When the applied force is 0, if the applied force is 0, that means when we have just started to apply the force, that means the force was 0. This length, original length was L, that means there was no deformation. The deformation or the elongation, I can say here, elongation was 0. And when the applied force is F, if the applied force is F, the elongation is L. Now as the force is a variable quantity, we have to take the average force. So work done, what is work done? That means the average force into displacement. We know what is work. Work means force into displacement, but here as the force is a variable force, we have to take the average of this force. That means 0 plus F by 2. Now why did I do 0 plus F by 2? 0 force means no elongation, F force means elongation. So average force acting on the body was 0 plus F by 2. Any variable quantity has to be handled in this fashion. Average force or the average value. The displacement here will be the elongation, that is small l. So 0 plus F by 2 into small l. So what is F by 2 into L, or half FL? Now already we have studied about the Young's modulus, Y. Now what is Y? Y was stress by strain. So stress means F by alpha and small l by capital L, because elongation was small l and the original length was capital L. Stress was F by alpha, where alpha was the cross sectional area. Cross sectional area. In short, we had already studied CSA, cross sectional area. Now if we try to replace the value of F from this equation into this part, F from this equation into this part. Now what is F here? F is Y alpha small l by capital L. We are replacing this F into this F. So work done was half FL. I can write Y alpha L by L instead of F. That is half of Y alpha L square by L. This is the value of the work done, total work done. This is the value of the total work done, total work done. Now the work remains stored in the wire as potential energy. So if we are asked to find out the density or the energy density, now straight away we can move into the energy density portion. What is energy density? The work done by volume. Energy density means the work done by volume. Work done by volume. Now what is the work done? Total work done Y alpha L square by L alpha. So I think alpha gets cancelled. It becomes half of YL by L into L by L. Now what is YL by L? Already we know this is stress into strain. Why stress? Because here stress by strain. So Y L into L, L by L onto this side becomes the stress. So YL by L becomes the stress. So energy density or small w, you can write it as small w. That means capital W by the volume. So small w was capital W by volume. Now the previous calculation may seem very large, so you can calculate the value of energy density using calculus also. Straight away I can write dW is equal to F dot dl. That means the total elongation of the wire is supposed to be the aggregate of the infinitesimal elongations. Then for an elongation, dl of the wire, elongation was dl. This dl is the elongation, the force. So the work done dW is equal to F dl. Now what was the value of F from the Young's modulus equation? F was Y alpha L by L. In the previous page we had already derived this one, by L into dl. This is the value of dW. Now if we can integrate and find the value of the total work done, W is equal to integration of dW. That means integration of Y alpha L by L dl. Now this integration has to be made from 0 to small l. because expansion was from 0 to small l. Here the constant term y alpha and capital L comes out. So L real remains inside. Y alpha by L square by 2. On replacing the values also, the value remains as y alpha L by 2. You can write here half of y L by L into y L. So 1 L remains here, and alpha remains here. Or you can write it like this: y alpha L square by L. This was work. Now from this also we can find out L alpha, energy density. We are trying to find out energy density, or small w is equal to capital W by L alpha, half of y alpha L square by L alpha. Similarly, we can find out to be y alpha by L by L, sorry, into L by L, half stress into strain. The last topic of this chapter is stress strain graph. We have to first understand what is a stress strain graph, study the different points, the different sections of the graph. Very important to understand it. And second thing is necessity of this graph, necessity of the stress strain graph. So first we try to draw the graph. This y-axis and x-axis. The x-axis you can write is strain, and y-axis is stress. Now the reason for being strain plotted as the x-axis is, I've already told you, the strain is a more fundamental aspect than stress. That means strain is independent of stress. Strain is independent of stress. Now 0 to A, this is a straight line. Now this line slowly moves up and curves down. Again it moves in this fashion. You can also see this diagram in your book also. So OA, now the point just before the bending is B, the point at the top is C, this point is D. Suppose this be E and this be F. So we have got 5 points here. I am going to express or explain to you very explicitly. In the examination, you need not write so explicitly. You can find some book and try to write it in a very shorter way, shorter fashion. So there are 5 points and 5 sections of the graph. Now the first point, or rather the first part, OA. What is OA? First part is OA. Now if we look into the diagram, we can say that we can see that OA is a very much straight line. OA is a very much straight line. That means here stress is proportional to strain. As this is a straight line, which means that the metal follows Hooke's law. The metal is following Hooke's law because stress proportional to strain. Now the wire behaves like a completely elastic body up to this point A. So the body behaves, I can write behaves or acts like a completely elastic body up to point A. Now the second thing is that point A, we will discuss the graph in this fashion only. That means one sectional part and the end part or the end point. Now what does this point A denote? This point indicates proportionality limit. That means stress proportional to strain. After this point, Hooke's law is not followed. So this point can be called as a point of proportionality limit. proportionality limit, point of proportionality limit. Now after this we move into the section of AB. Now what is section AB? Now in this section the ratio of the stress and strain is comparatively less. As I've already said that up to the point A, stress proportional to strain, that means Hooke's law is followed, and after point A, Hooke's law is not followed. That is why point A is known as the proportionality limit, the point or the ending point where Hooke's law is followed, that is point A. Now if for point AB we can write that the ratio of stress and strain is less. Ratio of stress and strain is low. That means the ratio, when we divide stress by strain, the value of stress by strain is lower or less, which means that the metal does not follow Hooke's law. Now after reaching this section of the strain, if the stress is removed, then the wear will regain its original length. Now you cannot remove the stress, rather you can say we remove the external force. We try to remove the external force, then the stress also will get removed, then the wear will regain its original length, which means that the strain will again be zero. The stress and strain is low. What happened? So ratio of the stress and strain is low, and the point Hooke's law not followed, metal regains its original length. So the strain ultimately will become zero. Now point B. What does this point B? In some books you will see that point A and point B are the same. A is known as the limit of proportionality and B is known as the elastic limit. Point B is known as the point of elastic limit. You already know what is elastic limit. If you cross this limit, a permanent deformation will set into the body and that deformation will not be removed ever. So point B denotes the point of elastic limit. So this point indicates that in case of most metals, you can say that point A and B are the same, are found to be quite close to each other. In the case of glass, you can take the example of glass. In the case of glass, this point A and B are same. Point A and B are same. Okay. So in case of, I can tell one more example. Let us take the example of suppose rubber. Now what happens in rubber? Distance between A and B are quite high. A and B are separated very much. Those 2 points are not same for rubber. For glass, those 2 points are same, but for rubber, point A and B are different. Now we move on to the section of section BC. Point B was done. Section BC. What does this section means? In this section, stress divided by strain becomes even less, and the metal, because we have already crossed the elastic limit, even less, and the metal gradually loses its elastic property. So we can write that when stress divided by strain, stress is very low. Stress by strain is very low, and the metal gradually loses its elastic property. Metal loses its elastic property. That means when anything that loses its elastic property, we can tell that property or the metal to be turning into plastic. If it loses its elastic property and becomes plastic. Now, after reaching this section of the strain, if the stress is removed, then the wear is unable to regain its original length. The wear will not ever regain its original length as permanent deformation has started to set in, because we have already crossed the elastic limit. So, the wear undergoes a permanent deformation. Now, point C. We look into the point. Now, what is point C? Point C is the point, is called the yield point. Yield means accepting defeat. Is the yield point or the upper yield point? Clearly, if you can say, this is the upper yield point. At this point, the stress level is known as the yield stress. The yield point for most substances cannot be determined accurately. Now, what can be the yield point? What is yield point? That means the metal has surrendered to the external force. There is no more capability of the metal to regain back its original shape and size. In spite you have removed the force, in spite the external force has been removed, still there will be permanent deformation in the body. So the metal has surrendered to the external force. So point C, what we can write? It's called the upper yield point. Upper yield point, point of surrender. Now you move into the section, again the section, next section will be CD. Next section will be CD. What is this? What does this section do? In this section, you can say that stress divided by strain is negative. Why negative? Because in the graph we see that the slope is towards the declining phase. The slope is towards the declining phase. It is declining. It is moving downwards. So we can say that stress by strain ratio is negative. Stress by strain is a negative quantity. I think we have understood the explanation for being negative, the value of the modulus being negative, because from the graph we see that it is a declining slope. It implies that even if stress is decreased, strain will increase. So you have to learn this, the meaning of the term negative quantity. Here, why it is called negative quantity, stress by strain. You can write here, it implies that even if stress is removed. Now if you can, if we are confused with this statement that stress is removed, you can write external force is removed. As the external force is removed, stress also gets removed at the same time. So in one state I am stating that the stress is removed. Stress is the stress is, I can say, is decreased. You have to write decreased, because not decreased, the strain will increase. The strain will increase, because here the case is that the strain will be increased if the stress is decreased. Now after that we move on to the point D. Point D. Now what is point D? Now point D means, this is the lower yield point. You can write it, this is the lower yield point. Point C was the upper yield point. This point D is the lower yield point. And now if stress is gradually decreased after the strain reaches this point, the graph, you can see, if you can retrace back the steps, the graph DCBAO, it will not move or return along DO. Sorry, it will not return along DO but along DO dash. That means if the stress is gradually decreased after the strain reaches this point, the graph DCBAO does not return along DO, it will return along DO dash. That proves that already a permanent deformation has set into the body, because strain is not zero here if we can retrace the steps back, but the value of OO dash is a positive quantity. So there will be a permanent strain or permanent deformation stored in the body, set into the body. So this is known as the lower yield point. For bodies with nearly perfect elasticity, these points A and B and C are situated so close to one another that practically these 4 points can be assumed to be identical or at the same point. You can say that the points can lie on the same point, in which case for bodies with nearly perfect elasticity. Now line segment, again line segment DE. Now how does DE look? This is DE. DE. Now what does the segment DE tell us? In this section, stress divided by strain is the least. That means it is the minimum most value for the ratio of stress by strain, and the metal becomes completely plastic. I can say that stress by strain is least. That means the value is least, and metal becomes plastic, completely plastic. Now the cross section of certain parts of the wire becomes completely lower than the remaining parts. The part that means if the wire is hung and the weight is hung here, the wire starts to elongate, and some portions with the wire will be like this. Some portions, the cross sectional area will be reduced very much. Now after that, what happens if we try to increase the force or increase the weight on the rod much more than what it was in this case, then the wire can snap from any one of these weak spots. The wire will snap from a very weak spot. Now line segment D means stress by strain is the least and the metal becomes plastic. The cross section of various certain parts of the metals becomes comparatively very lower than that of the remaining parts, like this. Now point E. What is point E? This was the point E. We have reached the point E. This point indicates the breaking point. This point indicates as simple as breaking point. That means the point at which the wire or any other metal wire, it will break or tear off. The stress developed at this point in the wire is known as the breaking stress or the ultimate stress. So at breaking point, the stress is known as breaking stress or ultimate stress or ultimate stress. Now after that point, line segment EF. After that